The Pythagorean Theorem is kinda weird. If you walk along a tile floor, you might expect your total distance to come from counting the tiles between where you started and where you stopped. Or maybe you'd expect to count the tiles along the two natural directions. But in reality, you actually have to count all of these tiles, which extend outward from those directions. We're supposed to be dealing with distance, which is one-dimensional. But in order to do that, we have to use two-dimensional areas for some reason. But why? Why should these floating squares care about how their area adds up to make a bigger floating square? Most visual proofs demonstrate that this technique does work, but they don't tell us much about why it works. So in this video, we're going to rebuild the Pythagorean theorem from the ground up. And we'll do it by carefully thinking about how angles, distances, and coordinates all work together. First off, we need to stop thinking of the Pythagorean theorem as a rule about triangles, and instead see it as a kind of bridge between distances and coordinates. Because the Pythagorean theorem requires a right triangle, we can always draw that triangle centered on a grid, so that A and B take the roles of coordinates in the x and y directions, and C is the straight line distance back to the center. This makes what the equation is actually doing a little easier to see. It's connecting a coordinate description on the left side with a distance description on the right side. But this coordinate picture depends on us having two perpendicular directions to walk along. If we walk straight east, then we aren't walking north or south at all, and vice versa. So how does this fit into the more general case, where we want to see how two arbitrary paths add together? Let's walk along some straight line path, A, and then along some other path, B. We can see that the result is also just a path, which we'll call C. These paths are all vectors, which just means they have a length and a direction. We can write this as vector A plus vector B equals vector C, where a little arrow means we're talking about a vector instead of a length. What we want is a formula for the length of C that only depends on the vectors A and B. Playing around with things, we can see that the factors that matter are the length of A, the length of B, and the angle between A and B, which we'll call theta. The tricky part is that the direction of C also depends on these three factors. To understand how A and B interact, let's do a kind of mathematician's thought experiment to see what our two vectors actually know about each other. Pretend that we live in a universe where everything is defined from the vector A's perspective, and all measurements are made along the direction of A. This universe is basically just a one-dimensional number line, where A's tail is at 0 and its head points in the positive direction. From A's perspective, its direction is the only direction that exists, so the vector A thinks that it's just a regular number. Any point outside of this space can only be described relative to that number line. So if we want to see what some outside vector B looks like, the only measure we can use is the part of B that goes along the number line. A doesn't care about the part of B that goes perpendicular, so we can throw that part out and keep the rest. To picture this, we can draw a line from B straight down towards A and see where the lines intersect. This is like casting a shadow or projection of B onto A. So what is the length of this shadow? Well, we know that the shadow scales with the length of B, since a longer vector gives a longer shadow. But there's also a kind of angle factor, which doesn't depend on B's length. When A and B align, this angle factor is 100%, or 1, so the shadow is just B. When A and B are perpendicular, the angle factor is 0, since the shadow is 0. When the shadow starts going backwards, we can treat that as the negative number on the number line. So when A and B point in exactly opposite directions, the angle factor is -1. Mathematically, this angle factor is just the cosine function, so we can write our shadow formula as the length of B times the cosine of theta. But really, you can just think of cosine as a measure of agreement, where you put in the angle between two directions, and you get out a percentage that tells you how similar those directions are. By the way, this shadow picture is essentially what a coordinate is. It's just the part of a vector's length that goes along some direction. So now, we have a way to measure B relative to A. But this formula doesn't consider the length of A. So far, we've been treating A and B as two different kinds of objects, where A acts like a direction and B acts like a length. What we really need is a way to measure not just how much B contributes to A or vice versa, but rather how much A and B work together. Let's take a closer look at how things work in this number line universe. In general, we can think of shadows on the line as a way to convert vectors into regular numbers, so that we can do one-dimensional math with them. And this isn't just an algebraic trick. When you remove the effect of direction, vectors really do behave exactly like numbers on the number line. The only catch is that these shadow numbers, as I like to call them, only work along one direction at a time. If we instead look at the shadow of A onto B, we get a different number, because we're using a different number line. Ideally, we want to mix our vectors together somehow, so that we end up with a single number that measures how they scale as a pair. Thinking about this as a kind of total effectiveness, if either vector doubles in size, we expect the result to double as well. And if both vectors double, we're doubling twice, so we expect the result to quadruple. Also, if either vector goes to 0, we want the result to go to 0. An input of 0 means that either our number line or the thing we're measuring has basically disappeared. Lastly, since neither vector should be special, their order shouldn't matter. If we just add our shadow numbers together, then we don't get these properties. But if we think about how we would do this with real numbers, it's easy to see that what we actually want is multiplication. If we multiply two numbers a and b together, then we get all of the behaviors that we're looking for. But remember, since the length of a and the shadow of b are already just regular numbers from a's perspective, a times the shadow of b is also just a number. This gives us a new kind of shadow multiplication, and its formula is just a times b times cosine theta. And now, we have something that acts like regular multiplication, but that also makes use of the angle. We'll denote this new kind of multiplication using a dot, and we'll call it the dot product. Notice how the dot product mixes all three factors that we care about together on equal footing. Because each factor is just an independent regular number, the math doesn't care what order we multiply them in. This means that we can use the dot product as a measure of how much two vectors agree, where neither vector gets special treatment. Geometrically though, this is a bit counterintuitive, since we already know that the shadow of A onto B looks different than the shadow of B onto A. So how do two different shadows end up giving us the same measure? Let's start by visualizing A dot B using our dot product formula. Whenever we multiply two lengths together, like A and B here, we can represent it as an area. If we take the shadow of B and stretch it out by the length of A, we end up with a rectangle. When the vectors are perfectly aligned, the rectangle's area is just A times B. But when they're at an angle, using the shadow of B automatically scales the rectangle down to match our formula. Note that for negative values of cosine, the dot product is also negative. Visually, this happens when the shadow points backwards, creating a rectangle that extends away from the base vector. We can look at how this area changes as the different factors change. If we instead project A onto B, then we end up with a rectangle that looks different, but from our formula, we know that both areas must be the same. There's actually a really cool trick that shows how we can go from one rectangle to the other without changing the area. First, we can shear the top rectangle down, so that its bottom side shifts onto B. If you imagine the rectangle as a sliding deck of cards, you can see that shearing doesn't change its area. We can also get the same effect by just slicing a triangle off the top and moving it to the bottom. Next, we can rotate this parallelogram by 90 degrees, so that the B side goes down to our copy of B. Again, area is preserved, since we're just rotating. Lastly, we can shear the parallelogram downward, so that it lines up with the second rectangle. This proves, visually, that the dot product doesn't care about order. A dot B and B dot A are the same thing. So now we have a literal area of agreement, a rectangle whose size depends only on the length of A, the length of B, and the angle between them. The nice thing is that the dot product still behaves like a regular number. This area is just a visual representation of treating A and B as numbers, then multiplying those numbers together. Now, instead of seeing how much two different vectors agree, what if we ask how much the vector A agrees with itself? That quantity is A dot A. A's shadow onto itself has length A, and the height of the rectangle is also A, so we get a square with area A squared. And this shows us the secret at the heart of the Pythagorean Theorem. When a formula has a squared length in it, it's a hint that a vector with that length is basically shaking hands with itself to measure its own agreement. Now that we understand how shadows and dot products work, we're ready to see where the Pythagorean Theorem comes from. Let's apply our new tools to the general path problem with vectors a, b, and c. If we can find an equation for the length of c, then the Pythagorean theorem should just be a special case. As we saw, the way you convert vectors into numbers is by casting shadows. And if you want a number that measures vectors objectively, without special treatment, you use the dot product. So, since finding the length c means measuring the vector c, we should start by taking its dot product with itself. We can visualize this by taking the shadow of c onto itself, then stretching it outward so that we get a square with area c squared. Next, we want to know how a and b contribute to c. Looking at the projections of a and b onto c, we can see that the shadows always add up to completely cover c. Mathematically, this is because projections obey the distributive property. When we split a vector up into parts, the shadows of those parts still match the shadow of the original vector. If one of the shadows goes negative, then the overlapping parts just cancel each other out. And since we're extending both of those shadows by c, we end up with two rectangles, representing the dot products a.c and b.c. Because the areas of these rectangles add up to the bigger square, we can write that a.c plus b.c equals c.c. Algebraically, all we just did was dot both sides of our equation with the vector c. Now, this formula looks nice, but it's actually difficult to work with. If we wanted to calculate a.c, we need to know the angle between a and c, but so far, we don't have a clear way to get that angle. Luckily, we can use our shearing trick to get a different picture for a.c. This gives us a rectangle where one side is a shadow of c onto a, and the other side is just a. If we look carefully, we can actually see how c's shadow is split into its a and b parts. One part is the shadow of a onto itself, creating a square, and this represents a.a. The other part is the shadow of b onto a, which gives us a rectangle representing a.b. So the total area of a.c is just the square a.a plus the rectangle a.b. Looking at the equation, what we just did was expand the vector c into a plus b, then distribute the dot product across it. And if we shift our split rectangle back onto c, we can see how this happens, since the a and b parts get transformed separately. We can use this shifting trick again with the b side, and we see that b.c is equal to b.b plus b.a. Remember, we know that the areas of the two rectangles off the sides add up exactly to the square off of side c, which is the same thing that our equation is telling us. Next, since the formula for the dot product doesn't depend on the order, a.b and b.a are the same thing, so we can group them together. If we simplify everything, then we end up with a squared plus b squared plus 2a.b equals c squared. And you might recognize this as the law of cosines, just written in a different way. If you want to see how, you can pause the video. But for our purposes, this is just the general distance formula for adding two vectors together. Now, you can probably see that we're very close to the Pythagorean theorem, but we still have this extra 2a.b term to deal with. For the final step, let's watch what happens if we gradually make a and b perpendicular to each other. As we change the angle, a.b and b.a go to 0, since the shadows of a and b onto each other disappear. And with that, we arrive at our final result. A squared plus b squared equals c squared. And we can actually see how the standard visual proof is just a special case when a and b are perpendicular. But this time, instead of being unrelated floating shapes, these squares represent the projection of each side onto itself. There you have it. We derived the Pythagorean theorem by converting vectors into shadow numbers. So now we can answer our original question. Why does the Pythagorean theorem have squares in it? We started by seeing how c measures itself using the dot product. Since its components, a and b, are perpendicular, their shadows essentially ignore each other. So c's total agreement with itself is just a's agreement with itself plus b's agreement with itself. And geometrically, a vector agreeing with itself is just a square. The cool thing is that we got here just by carefully thinking about how to compare two vectors. And that led us to discover the dot product as the natural way to convert vectors into numbers. It turns out that the dot product is also useful outside of geometry, in places like physics, computer science, and any situation where you can represent things as vectors. I hope you've seen that when you really focus on understanding basic concepts like direction and multiplication, more advanced ideas like the dot product tend to just pop out as natural next steps. Lastly, I'd like to give credit to Stack Exchange user Toph for the algebraic outline for this approach. I'll leave a link to their original comment in the video description. If you enjoyed this video, it would be a big help if you can like, subscribe, or share it with someone else who might appreciate it. Thanks for watching.